This is a Simulink circuit on how you can generate DSBSC using a switching modulator. The message signal is a sine wave. I set it to have an amplitude of 2 and to have 1000 samples per period. And for a frequency of 2 Hz, it's going to have a sample time of 0.0005 seconds. The pulse generator block has an amplitude of 1, also with 1000 samples per period. And the pulse width is 500. That means the duty cycle of this is 1/2, and this is precisely a square wave. And for it to have a frequency of 20 Hz, the sample time is 0.00005 seconds. The circuit has a sine wave as the message signal. The pulse generator makes the rectangular square wave. They are both passed into a product block, and then we could run this first to see what we get so far. If we look at the spectrum of the sine wave, we'll have spikes at 2 Hz and -2 Hz. This is the spectrum of the square wave. The center spike is harmonic 0, or the DC offset. And this is the fundamental frequency spike. And then since the square wave has a duty cycle of 1/2, every second harmonic is going to be missing. After taking the product of the message sine wave and the square wave in the time domain, we're going to have this spectrum, which is the convolution of those two signals in the frequency domain. To get the DSBSC modulated signal, we want to keep the sidebands at 18 Hz and 22 Hz, as well as -18 Hz and -22 Hz. So these two spikes and these two spikes. We want to attenuate everything else, including these center two spikes, which is from the carrier. So this is why it's called a double-sideband suppressed carrier modulation. So to keep these two spikes and these two spikes, we're going to pass this through a bandpass filter. So these are the parameters I use to set the bandpass filter to keep the spikes I want. And this is the frequency spectrum of the modulated signal. So as you can see, we kept this sideband and this sideband, and we suppressed this carrier. I wasn't able to suppress it more. And then these are the signals in the time domain using the scope. So here we have our message sine wave. This is our rectangular pulse train, and this is the product of those two. So it's kind of like a sampled signal. And then after passing it through the bandpass filter, we have the DSBSC modulated signal right here. This is the circuit to generate DSBSC using a switching modulator on ORCAD. All the components used in the circuit can be found by going to Place, PSpice component, and I used the resistor, inductor, and capacitor. And for the transistor, I went to discrete and got an NPN. The two sources I used are both sine waves. The first sine wave I set to 20 kHz and an amplitude of 1. This one's going to act as the message signal. The second sine wave has a frequency of 200 kHz and an amplitude of 3. And the way the circuit works is we're going to have this message signal here going to go past this resistor, and this switching source is going to go into the gate of the BJT transistor. And when this signal is high, it's going to create a virtual ground from here to this node. And when this signal is low, this message signal can pass through. So at this node, it generates what looks like a sampled sine wave that we see earlier from multiplying a square wave and this message sine signal. And then after this 20K resistor, we're going to have this inductor and this capacitor in parallel to create a bandpass filter. And at this node, that's going to be the DSBSC signal. So let's run it. Okay, so remember this green voltage marker and this red voltage marker. Alright, so this green trace is the result of switching the BJT transistor on and off to create that virtual ground at the message signal. And then this is in a similar appearance to the message sine wave being multiplied to the square wave in the time domain. And then after passing the signal through the bandpass filter, we're going to have the DSBSC signal right here.